Good afternoon, everyone. Today I'm presenting.
We download your presentation and permission to play your
Yeah. Let's give me. Yeah. Okay. Today I'm presenting this paper, SadTalker, Learning Realistic 3D Motion Coefficients for Stylized Audio-Driven Single Image Talking Phase Animation. So long name. It was presented in CBPR 2023. So this paper addresses those challenges to overcome natural and unnatural movement. So the model, the meaning of paper is to animate the portrait of the person given the audio. So they try to overcome unnatural movement, the distorted expressions, an identity issue in talking head videos generated from single image and audio. They propose SadTalker, leveraging 3D motion coefficients to in between to 3D motion coefficients, headphones and expressions for realistic animation, avoiding pitfalls of 2D motion fields and stiff 3D expressions. Key technologies they invented are XNet and POSVAE. XNet is to extract expression coefficients from audio. POSVAE is to extract pose coefficients from audio. So the task is given an input audio and portrait of person. Talking head portrait animation is to synthesize video frames of the person and expressions are synchronized with audio signal. There are like challenges in this task because the audio and the expressions of the person is not like one-to-one connection. And there are limitations in existing methods. Existing methods use facial landmarks, 2D flow-based, latent-based. They use mostly 2D latent variables. So it has like limitations in disentangling head motion and expressions. This method approaches talking head video generation using 3D coefficients, 3D facial models for highly decoupled expression for different types of motions. So main contributions of this paper, the SadTalker, the novel system to synthesize audio-driven single image talking face animation, to learn realistic 3D motion coefficients of 3D models from audio. XNet and POSVAE are presented individually. A novel semantic disentanglement and 3D aware face renderer is proposed to produce realistic talking. So these two are to extract the 3D coefficients from the audio, and there is a renderer to render these coefficients back to the video. Experiments show that they achieve state-of-the-art. Related works in this field is audio-driven single image talking face generation. Early works focused on accurate only to generate lip motion, not any expressions or head movement. For example, at TV, GNet, Make It Talk use facial landmarks for intermediate representation with Make It Talk also disentangling content and speaker information. And there are also some previous 3D 3D morphable model-based methods encountered, but there are issues with inaccurate expressions and artifacts in the generated videos. And another related task is video-driven single image talking face generation, known as face reenactment or animation. Compared to this task, it's much more easier because it has like a driving animation already. And just to transfer motion from source to target person. They also that line of work explored landmark-based, unsupervised landmark-based, and 3D MM-based and latent animation methods. And SadTalker's face renderer, the last stage, is inspired by unsupervised landmark and 3D MM-based methods, but focuses on generating realistic motion coefficients. We will see that. The overview of the whole model is it consists of like three different subnetworks. There is three different subnetworks, like two of them POS-VAE and X networks to extract coefficients, POS-VAE and XPNet to extract expression coefficients, beta n, and n means the number of frames, beta is expression coefficients, rho is head pose coefficients. So POS-VAE in XNet is used to extract expression coefficients and head pose coefficients from audio and like input image, the new image portrait. And there is 3D aware face renderer. We feed the extracted expression and head pose coefficients and expression and head pose coefficients of the source image, and it renders the video. So some words about 3D face models. Why we use 3D models for this task is to enhance the realism of generated videos, because the videos are captured in 3D environment. Previous works not considered 3D space much. 3D morphable models is used as intermediate representation for more accurate modeling. Okay, what is that 3D MM? 3D can be expressed using this equation. S is equal to S bar plus alpha UID plus beta UXP. S bar is average shape of 3D face, like average for all humans. Then UID and UXP is a matrix, consists of orthonormal basis for identity. UID is for identity and UXP for expression. And alpha and beta are vectors to store the coefficients for identity and expressions. And this express this to express the 3D face shape, and we have R and T to express head rotation and translation. T for translation, R is for rotation. The pitch, yaw, and the angle. Focuses, this model focuses on modeling motion parameters. Beta, beta is this coefficients for expression basis, and R and T from audio. Like these three are generated from audio, and this alpha comes from the source image. So XPNet, this is the architecture of XPNet. It consists of audio encoder. Audio encoder is just MLP. And mapping is also MLP. It generates beta, the vector that expresses the expressions of the person. And after encoding the audio from mass spectrogram, We also add beta zero. This comes from the beta zero comes from the source image to reduce the uncertainty of identity. So we're providing the beta zero, so it doesn't produce very like spread expression. Then we can z-blink is controllable variable from model to control the blink of person, blink of eyes. And this XPNet has three loss functions. So we have wave to lip. Wave to lip is the previous model that produces lip motion, only lip motion from audio. Wave to lip motion is used to to distill its knowledge to learn the lip motion for XPNet. This RE is pre-trained 3D MM model to extract the expressions and other coefficients from the result of the wave to lip. And yeah, this lambda this still comes from wave to lip, and we have RD. RD is differentiable but without learnable parameters. It is 3D face render. It renders like 3D face from the expressions and the identity coefficients. And based on that 3D render, we have red and landmark loss. Lambda red is lip. Lambda red is lip reading loss. It's just an, I think, MSE loss. Yes, MSE loss. Between lip, only considers lip, just first crops out the mouse and considers the lip points. And landmark loss is just the whole 2D landmark loss. Actually, after rendering, they converted back to the 2D, then used landmark loss. Landmark loss consists of like landmark of the face, the points around the face, and the main points for mouth and eye. This is pose VIE. To XPNet just generates beta, the expressions. Pose VIE generates pose coefficients at raw. It is based on VIE or conditional VIE. It learns residual of the input, like probability distribution of residual of the input head pose, P0 via conditional VIE. So the conditions, this gray is conditions. Conditions are first frame style identity, Z style, and the audio clip, like T frame audio clip. After training, we learn here encoder and decoder is also this MLPs. I think like several layers of fully connected layers. And after training, we learn this mean and standard deviation of, actually we learn the probability distribution of residual of pose, delta P, and during test time, we don't need all this delta P for all frames. We just need this condition, and we generate from this sample, from the probability distribution we learned, the sample, and we use condition. And we have also three loss functions here. They are basically most like VAE loss functions, variational autoencoded loss functions, fullback labor divergence to match the learned probability distribution to the decided probable distribution, for example, Gaussian distribution, and MSE and GAN loss functions are used to how like how efficient it reconstructs the residual. Then the second stage of the model is to render the face, actually render the video. It is based on face video to video, like as we saw in the beginning. It's based on the face reenactment model. This is face video to video models architecture. It works with source image and driving image. Driving image comes from video, we wanna reenact, and source image is the new portrait. But in this task, we don't have driving image, so we change this part. So we generate this. So it works. So they produce XC, XS, and XD. Oh. Human source image and driving image face with generates motions in unsupervised 3D key point space. Yeah. This face to video with generates motions in unsupervised 3D key point space. They are represented by these 2, 3 matrices. Then image can be generated via appearance and the key points. Then with 3 key points and appearance, we generate videos. So here to generate key points, we use our face reconstruction model for XPNet and POSNet to POSVAE to generate beta and raw n. Beta 0 raw 0 comes from source image. Using 3D face reconstruction model, just some pre-trained model, and this is our XPNet and POSVAE to generate beta n and raw n, and there is some mapping net. I think there are also some formations of MLPs. Yeah, it is network with 1D convolution and mostly 1D convolution and MLPs. Then we have motion in 3D key point space, and appearance comes from source image, and we can generate the videos. This part is similar to the face feed to it. For the experiments, for training, they used voxel dataset, contains 100K videos of more than 1,000 subjects. They cropped videos to make like person in the middle and resized to 256 by 256. Then these videos used to train face render. As they say, some videos and audios are not aligned fully, so they drop that samples to train POSVAE and XPNet because they are more prone to learn only the expressions, so they should be like aligned. Videos and audio should be aligned. And for testing, they used HDTF. This should be 3. I'm sorry. Like it has 346 videos, and they only used first 8 seconds. Yeah. To evaluate the model, they use FID, per inception distance, for realism of generated videos. Like it's used to compare like like inception distance between the generated video and original, and cumulative probability blur detection for sharpness, cosine similarity for identity preservation, and yeah, they use lip synchronization and mouse shape to evaluate lip synchronization and mouse shape. They evaluate the perceptual difference of the mouse shape from wave to lip, because wave to lip is that model is only like animates the lip motion, so it is more accurate. So I think they just compare to that model. This is like quantitative result comparison to other state of the art models. As they claim, they have better head motion and video quality, like in terms of FID, like blur or cosine similarity, and head motion diversity and beta line. But in terms of lip synchronization, they're not like better than not better than previous models, because there are some models, for example, wave to lip model is to they just generate lip, so they're sure better than this model in terms of lip synchronization. And yeah, there was video. I'm sorry, uh, I cannot show it. I think I had to give access to from my computer. They used user study to kind of compare the other models in terms of the human perception. They used 20 videos and 20 participants. They marked like the best method in terms of four categories: video sharpness, lip synchronization, and diversity, and naturalness of head motion, and overall quality. And yeah, they claim their model is better in terms of like even in terms of lip synchronization. Um, yeah. And the model's limitations. It has very much limitation in teeth and eye realism, because 3D MM models doesn't contain not much information, does not contain much information about teeth and like fine details of eye. It just contains like expression, like points to express this face. So they have like very blurry teeth in some results. And as we saw in the XPNet, the loss functions are mostly focused on lip motion, neglecting other facial expressions, so such as emotion and gaze direction. As a result, generated videos has fixed emotion, reducing the realism of the generated content. So they claim they acknowledge that limitation in tease realism and fixed emotion can be considered as future work. And yeah, they want as a future work, they potential enhancements in modeling facial features and expressions for more comprehensive and realistic synthesis. Yeah, that's all. Yeah. Then another facts about this model is their GitHub repository has around around like 9,000 stars and more than like 1,000 forks, and I think like it's kind of well accepted research work compared to I like saw the other papers around this topic, but not many of them are accepted from community. And yeah, they have like GitHub Discord server, and yeah, their work is kind of they also build applications around it, and you can find like videos in YouTube generated by other users. Yeah, thank you for listening. Any questions? No.